Welcome to the Organic Chemistry, the second part of Chemistry 2 lecture. And today is our first lecture, and before we start, I would like to briefly introduce you into the topics you can expect from this lecture. We have three main focus topics, and the first one is alkenes and alkynes. And more specifically, we focus on electrophilic addition and pericyclic reactions. And this topic is mainly described in chapter 21. And our second focus is benzene and other aromatic compounds. And here we will have a closer look on electrophilic substitution reactions, which can be found in chapter 22. And the last focus will be aldehydes and ketones. And here we will understand the nucleophilic addition and alpha substitution reactions, which can be found in chapter 23. And before we start with all these topics, it is important that all of us are on the same level. So today we will have a revision lecture that you can briefly revise everything you learned in Chemistry 1. And here it is important that you personally check if you have the knowledge you should have, and if not, that you revise it based on the book or your former notes from the lecture Chemistry 1. And we will have to revise mainly chapter 5, 18, 19, and 20. And important here is in chapter 5, the hybridization of carbon atoms, and then also in chapter 18, the isomerism and stereochemistry, chapter 19, organic reaction mechanisms, and here especially nucleophilic addition and alpha substitution reactions. And then in chapter 20, halogen alkanes and substitution and elimination reactions. So, as you already know, let's say the central atom of organic chemistry is carbon. So always when we talk about organic chemistry, we mainly talk about carbon-hydrogen bonds or carbon-oxygen, but carbon is always involved. And carbon is a special element. It is in the second row of the periodic table, and then it has, based on this, two s and two p orbitals, which are partially filled. And as you know, it is in the first main group of the periodic table, so you will expect to have 4 valence electrons at carbon. And as you discussed already with Luke in the inorganic chemistry lecture, you know that there's the possibility for a hybridization. And especially for carbon, we often discuss the sp3 hybridization. And what means sp3 hybridization? It is the interaction between 2s orbital and 3 2p orbitals to form then 4 sp3 hybrid orbitals. And if we have a look on the scheme here, you can see the 3 different 2p orbitals. It is 2px, 2py, and 2pz. And as you know, we also have this 2s orbital. And then they interact and form these 4 sp3 hybrid orbitals. And what is important, it is that if you give, let's say, 4 orbitals in, which interact, then you also form 4 orbitals as hybrid orbitals. So you should always give the same number in as you get out. And then if we talk about sp3 hybridization, it is important to remember that the angle of these sp3 hybridized orbitals, when they form a bond, it is always a tetrahedral binding situation, so the angle between the different bonds are 109.5 degrees. And if we have a look on this energy scheme here, we can see the starting point. So we have this carbon atom with 2s orbital and then 3 different sp orbitals, which are partially filled. Then we have this interaction form the 4 sp sp3 hybrid orbitals. And as you already see, the total energy of the sp3 orbitals is the same as the total energy of the 3 p orbitals together with the s orbital. And this is really important that you always remember this. And then also here you can see that the 4 sp3 hybrid orbitals are exactly the same in energy. So there's no difference between 4 sp3 hybrid orbitals. They're identical. And yeah, what can we now do with this sp3 hybridization? We can, for example, use the sp3 hybridization for explaining the binding geometry of alkanes. And alkanes, as you already know, are the simplest hydrocarbons, and they only or mostly only contain carbon-carbon single bonds and carbon-hydrogen single bonds. So if we now want to have a quick look on alkanes, if we now, for example, start with methane, the simplest hydrocarbon, we know that we have a carbon atom with 4 sp3 hybridized orbitals, and these orbitals are here indicated as purple, and they are arranged around the carbon to form this tetrahedral binding angle. And then we see that we have 4 carbon-hydrogen sigma bonds, and each carbon-hydrogen sigma bond is formed from an interaction between an sp3 hybrid orbital of the carbon atom and one s hydrogen orbital. And then the formed or the resulting sigma bond contains 2 electrons. And we have this 4 times, so finally we end up with 4 identical covalent carbon-hydrogen sigma bonds, each containing 2 electrons. And thanks to the tetrahedral geometry, we then minimize the repulsions between the electron pairs in the 4 sigma bonds, while at the same time we maximize the strength of each bond. So in other words, it is very favored for methane to make the bonds out of the sp3 hybrid orbitals, and if not, the energy of this molecule would be higher, so it would be less stable. So this is the absolutely preferred geometry. And if we go to another alkane, we can, for example, go to ethane. And for ethane, we have a similar binding situation, but now we have not only 1 carbon atom, but 2. And the 2 carbon atoms are both tetrahedral coordinated, and then they're linked to each other with a carbon-carbon sigma bond. And what do we know? We know that both of the carbon atoms are sp3 hybridized, and then we can form 3 carbon-hydrogen sigma bonds between from the interaction between the sp3 hybrid orbital and the hydrogen s orbital. And then, the carbon-carbon sigma bond is formed from the interaction between 2 sp3 hybrid orbitals. And also important is have a look on the energy diagram here for this methane, for example. So we start with the atom orbitals of the carbon, which is sp3 hybridized, and with the hydrogen, which has 1 s orbital. And then we make the bonding. That means we form the molecular orbitals, and for the carbon-hydrogen bond, which is the sigma bond, and you can see lowest molecular orbital gets filled with the 2 electrons, and then the sigma star antibonding molecular orbitals remains empty. And if you now wonder if sp3 hybridization is only restricted to organic molecules, I can answer you no. For example, ammonia also shows this sp3 hybridization for the nitrogen atom. And as you can see here, we have this ammonia molecule, and the geometry is tetrahedral. And tetrahedral, as we count this lone pair also as a kind of sp3 hybridized orbital. And the electronic configuration of nitrogen is 1s or 1 and if you now wonder if sp3 hybridization is only restricted to organic molecules, I can answer this question with no, because here you can see the ammonia as example for a non-organic molecule, and we also observed sp3 hybridization. The electronic configuration of nitrogen is 1s2, 2s2, 2p3. So in total, we have 5 electrons in the 4 sp3 hybrid orbitals. And 3 sp3 hybrid orbitals interact with 1s hydrogen to give the sigma bonds that each contains 2 electrons. So 1 electron comes from the nitrogen and 1 electron comes from the hydrogen. And then we have 1 sp3 hybrid orbital that contains 2 electrons from the nitrogen atom, and this is the lone pair. So you can see this here. And the lone pair can, on the nitrogen, can, for example, then interact with a proton to form nitrogen hydrogen 4 plus, which explains the basicity of ammonia. And if we have a look on the energy profile, you can see again a very similar picture as already seen for the carbon atom. So we have the ground state of the nitrogen here with 2s orbital and 2p orbitals. And then we have this interaction to give 4 identical sp3 orbitals, hybrid orbitals, and then we fill the 5 electrons inside the sp3 hybrid orbitals, and then you can see this completely filled hybrid orbital, which means we have 2 electrons inside, and this is then the lone pair of the nitrogen. The other 3 sp3 hybrid orbitals can still interact with the hydrogen 1s orbital to form the nitrogen-hydrogen sigma bond. And now we go to the sp2 hybridization. And sp2 hybridization means that we combine 2s and 2px and 2py orbitals to form 3 identical sp2 hybrid orbitals. And these are in one plane at 120 degrees to each other. And important to see here is that we would have a third p orbital, the pz, and this orbital is not involved in the hybridization, so this means this pz remains unhybridized. And if we look now at the orbitals, you can see here the starting point, and then we have the interaction to form this sp2 hybridization, and then we end up with 3 different hybrid orbitals. And if we now have a look on the energy diagram, we can start with the ground state of carbon. So we have again a filled s orbital, and then 2 3 sp orbitals, whereby only 2 orbitals are filled. And then we have this interaction to form the hybrid orbitals, the sp2 hybrid orbitals, and the 2pz orbital remains unhybridized. So we just draw a horizontal line, and the energy of this orbital will not change. Conversely, the energy of the 3 sp2 hybrid orbitals are exactly the same for each of these orbitals, and the total energy of the 3 sp2 hybrid orbitals is the same as the total energy of the s and 2 of the p orbitals. And yeah, for what can we use this sp2 hybridization? For example, for alkenes, ethane, for example, then we can see that we have three sp2 hybrid orbitals around the carbon, and the pz orbital remains unhybridized. And the sigma bond is then formed between two sp2 hybridized carbon atoms, and the sigma bond contains two electrons. Then we have two remaining sp2 hybrid orbitals on each of the carbon atoms, which interact with hydrogen s orbitals to give sigma hydrogen bonds, and each of the sigma carbon hydrogen bond contains two electrons. And then we still have the pz orbital, one on each carbon atom. And these two pz orbitals then finally combine to form the pi bond, which results in electron density above and below the planar sigma bond framework. And how this works we will discuss more detailed in our chapter for alkenes, but you already know the very basic situation now of the pi bond. And what is important here to know is that the carbon-carbon sigma bond is stronger than the carbon-carbon pi bond. And the last hybridization we still have to revise is the sp hybridization. And sp hybridization results from the interaction of two s and two pz orbitals to form two identical sp hybrid orbitals, which are directed at 180 degrees to each other. So we can also say we have a linear coordination of the molecule. And if we look here, so we have the starting point, and we end up with these two sp hybrid orbitals, and then we can have again a look into the energy diagram, and you can see that based on these interactions for the sp hybridization, we end up with two sp hybrid orbitals, and the energy is now lower than the former energy of the three p orbitals, but higher than the starting point energy of this s orbital, so it is in between. And for the hybridized px and py orbitals, we remain the same energy. And for what do you need this sp hybridization? For example, for explaining the binding geometry of alkanes. If we now look briefly at ethane, then we know that ethane has a triple bond, and this triple bond can be explained with the sp hybridization. So first of all, we start with the interaction between two sp hybrid orbitals of the two carbon atoms, which then yield this carbon-carbon sigma bond. And then the remaining sp hybrid orbital on each of the carbon then interacts with the hydrogen s orbital to give a carbon-hydrogen sigma bond on both sides. But then finally we still have two spx and spy orbitals which are unhybridized on each carbon atom. And these two orbitals can then interact to give two pi bonds, which are arranged at 90 degrees to each other. So then what shall we remember is that we have one sigma bond and two pi bonds. And again, the sigma bond is stronger than the pi bond. And you can directly test your knowledge with the end of chapter question from chapter 5, exercise 10 and 11.